All right, so our second speaker of the afternoon is Sebastian Degen to tell us about how almost all q-matroids are not representable. Please.
Oh, you can hear me? Okay. Okay, let's start again. So I will continue the journey into the q-matroids. And in my talk, I will show you the recent results of a joint project with my advisor, Lucas Kühne, concerning the asymptotic behavior of representable q-matroids. So there will be 4 parts. And in the first part, I will quickly go over the background. We already saw a lot of q-matroid concepts, and I will recall them, most of them for you, and I also add new concepts to it. Then in the second part, I will show you my main results. And in the last 2 parts here, I will talk about the proof strategy of the main result and what concepts we have to use in the strategy. Okay, then let's start the background. And let me recall what is the motivation for q-matroids, or why we care about q-matroids. And there's a very nice slogan, which is kind of the first informal description of q-matroids, saying that you can view q-matroids as q-analogs of matroids. So what do I mean with q-analog? By q-analog, I mean the process if we generalize from finite sets to finite dimensional vector spaces, and most of the time over finite fields. So for simplicity, we just consider fq to the n throughout this talk. And looking at that slogan, the first motivation is kind of obvious. We want to define q-analog concepts of already existing matroidal concepts. But then the second motivation, as Daejeon already said, is that we can look at it from an algebraic coding theory perspective, which gives us representable q-matroids, which arises from rank metric codes, actually. Okay, so what is the general definition of a q-matroid then? First, let's fix the notation that whenever I write this expression here, I mean the subspace lattice with respect to the usual ordering, the subspace inclusion. And then having that, we can define a matroid as a pair, a q-matroid as a pair E rho, where E is our fqn and rho is a function from the subspace lattice to the positive integers, which we call the rank function. And this rank function should satisfy 3 axioms, which we already saw, but I recall them. So the first is that when the rank of every subspace should be bounded by its dimension. Then the second one is that whenever we have a subspace inclusion, x into y, the rank function should reflect this inclusion, meaning that the rank of x should be smaller equal to the rank of y. And lastly, there's the so-called semi-modularity property, just saying that the rank value of the intersection and of the direct sum of the inner vector space sum should be always smaller or equal the rank of the individual subspaces. And finally, having this axiomatic, we simply say that the rank of the whole q-matroid is the rank function evaluated in the whole space. And as you can see, these axioms are actually direct translations of the normal usual matroid axioms, where we have to replace the size, for example, by the dimension here and the union by the intersection, as we saw before. And a very nice example, as also 2 times was already introduced, is the uniform q-matroid, where I fix an integer between 0 and n, and the rank function is described via this minimum of the k we chose and the dimension of the input vector space. Okay, and these q-matroids actually behave very well under certain operations. So now, given that we have the general definition of a q-matroid, we actually, for our main result, want to yeah. Oh. Yeah. Yeah, this way. Okay. Now it's better? Yeah. Okay. Thank you. Sorry. Okay, now we are knowing the general definition of a q-matroid. We are actually interested in 2 special classes of q-matroids for our main result. And the first one is the so-called class of paving q-matroids. And all what I'm saying here is actually a direct Q analog of the usual matroid case. So in order to define a paving q-matroid, we have to define the notion of the circuit. So given a q-matroid M, the circuit is just a subspace such that all its proper subspaces have rank equal to its dimension. And having this definition, we can define a paving q-matroid as a q-matroid such that all the circuits have dimension greater or equal to rank of the given q-matroid. And we can actually construct a large class of these q-matroids via the following proposition due to Larsen and Jani from 2022. And the main point of this proposition is just the collection here of the k-space of fqn such that for every two distinct spaces we have intersection dimension smaller or equal k minus 2. Using this, we can define this slightly technical rank function, and it turned out that it satisfies the three rank axioms and therefore gives us a q-matroid of rank k. But not only that, also this q-matroid is paving because the circuits are all the spaces in S and higher dimensional stuff. Okay, so this is the first class we want to look at. Now the second class is the class of representable q-matroids, and as I said in the beginning, I want to use a slightly different definition here. I want to use rank metric codes, which induces these representable q-matroids. So what is a rank metric code then? So for this, we have to consider the vector space f q to the m for some field extension and endowed with the so-called rank metric or rank distance, which is defined for two vectors such simply as the rank of the difference of them. And with this ranked expression here, I mean that I take the fq dimension of the fq span of its coordinates. Okay, using this setup, we then define a rank metric code, or for short RMC, simply as an fql linear subspace of our given rank metric space here. And we not only care about the subspace itself, but we also care about its generator matrix, which is just a matrix such that the rows are actually generate our rank metric code. Okay, now how to go from the rank metric code to the q-matroid? This we can do via this proposition from Larsen and Jani in 2018. Saying that whenever we have a rank metric code and it's generating matrix, we can find the following rank function here, where we simply take the fq rank of the matrix product of the generating matrix of our code and of a generating matrix of our input space. And it can be shown that it also satisfies the three ranks axioms and therefore gives us a q-matroid of rank k, and the rank k is because our q code here is of dimension k. And we call this q-matroid the q-matroid associated to C. So we have associated to rank metric code a q-matroid, but we can also go the other way around, meaning that when we have a given q-matroid, we call it representable, or fqm representable, sorry, if we can find such a rank metric code for a suitable field extension, such that whenever we assign we built the associated q-matroid to this rank metric code, this should equal the original matroid, the q-matroid we are looking at. Okay, so this is all about the background. Are there any questions up to this point? If not, then I move on to the main result. And I actually want to talk about the two questions which motivated our studies. And the first one is from 2018. Sorry. The first one is from 2018 due to Larsen and Pelikan asking whether potentially all q-matroids are representable. But this turns out to be too optimistic, and the answer is no. Since, for example, Larsen and Jani soon after introduced the method of translating the non-representability of a matroid to a q-analog setting. For example, for the Varmash matroid, they defined the q-Varmash matroid. Okay, and soon after that, Uris herself, together with Seria, actually found the smallest non-representable q-matroid, which is in dimension 4 over the field of characteristic 2 and has rank 2. And let me note here that if you compare the smallest dimension to the smallest cardinality of a matroid, you see that the smallest dimension is smaller than the smallest cardinality of a non-representable matroid. 4 to 8, I would say. Okay, so knowing that the answer to the first question is actually no, we ask ourselves, is there a potential Q analog of Peter Nelson's theorem saying that asymptotically almost all q-matroids are not representable? And the answer is yes. And let me phrase our theorem in this way. So whenever we denote RQn the number of representable q-matroids and nqn the number of all q-matroids and fqn, then this ratio here asymptotically vanishes. So in other words, the portion of representable q-matroids tends to 0 as n grows to infinity. Okay, and then I now will present you the proof strategy and then talk about the concept we have to use for this strategy. So there are two tasks. The first task is to find the lower bound of the number of all q-matroids, which is at least double exponentially. And we want to use a codic theoretic concept named constant dimension codes for this. And then the second task is to find an upper bound on the number of all representable q-matroids, which is at most exponentially. And for this, we actually use the concept of zero patterns. Okay. Now then let me start with the lower bound. So as I said, we want to use the concept of constant dimension codes. In order to do this, we have to define what a subspace code is. And the setup for this is that we look at our subspace lattice and equip it with the so-called subspace distance, which is just given two subspaces. We sum up their dimension and subtract twice the dimension of the intersection. Using this, we simply say that the subspace code is a non-empty subspace of our subspace lattice. And if we choose all the subspaces in that subset C to be of the same dimension, let's say K, then it's called a K constant dimension code, or for short KCDC. So and why do we want to use this KCDCs? The maximal cardinality of such a KCDC can actually lower bound it. I will not go into detail with that, but we want to use this lower bound for an estimation on our number of all q-matroids. And in order to do so, we have to describe a connection between these KCDCs and q-matroids, and actually it turned out that it has to be the paving q-matroids. So what does this connection look like? So this connection relies on the theorem I showed you before, how to construct paving q-matroids due to Lösen and Jani. And let me recall what the main point was. The main point was this collection S of k-space and fqn, such that for every two distinct, we have a subspace dimension, we have an intersection dimension smaller equal k minus 2. And this will yields us a paving q-matroid. So using this result, we can prove the following Länge, saying that whenever we have a KCDC with the special condition that whenever we take two subspaces out of this set S, the subspace dimensions, distance should always be greater or equal to 4, then this is already enough so that S fulfills this condition here, and so this yields us a paving q-matroid. But that's not all. Note that whenever we take a subset of S, this subset also satisfies this condition here, and so also gives us a paving q-matroid. So this means that we have at least 2 to the power of the cardinality as many q-matroids out of a given KCDC. Now, using the estimation on the maximal dimension and this lemma for a specific subspace KCDC, we obtained this following result here, saying that whenever we have a dimension greater or equal to 4, then we can bound the number of all q-matroids from above by this following expression here, 2 to the power of q to the power of some exponent v1n, which I do not write out, but it is really ugly. But let me just say this v1n is a polynomial in n, and it's always greater or equal to 0 for all n. But if you note here, this is actually a double exponentially bound, and so we completed our first task. So we bounded the number of q-matroids in the way we want to. Leaves us with the second task to find an upper bound to the number of all representable q-matroids. And for this, as I already said, I want to use the concept of zero patterns. So what is a zero pattern? In general, really short. So let K be a field, and we fix a field element, and we find delta of A to be 0 if A is 0 and asterisk otherwise, so we don't care about the value when it's not 0. And then if we have a sequence of polynomial and some polynomial ring in S variables, and we take an element of the vector space K to the S, this expression here will be called a zero pattern. So it's just the evaluation of every polynomial in A and then evaluating delta in all of these values. So why do we care about the zero patterns? So similar to the subspace code case, the number of zero patterns can actually upper bound it. And this upper bound depends on the degrees, the various degrees of the polynomials in our sequence. And also, I will not go into details with that. But we want to use these estimations for our number of all representable q-matroids. In order to do so, we again need to relate zero patterns to representable q-matroids. And I will also not go into detail with that because it's quite technical and I will not have enough time for this. But let me simply say that we want to use Eurus and Pelikan's result I showed you before, how to associate to a rank-metric code a q-matroid, and especially want to use the generating matrix, which we fill with a number of indeterminants and then look at the determinants to construct the sequence of polynomials f. So if you believe me that this is true, we gain the following results. So whenever we have a dimension greater or equal to 2, and we have a rank between 0 and n, then the number of representable q-matroids of rank k can be bounded in 3 different ways, depending on the rank. So if k is 0 or n, then we only have one q-matroid. It is representable, and it is the uniform q-matroid 0n and nn, or also called free and trivial q-matroid. If we end the case as k is 1 or n minus 1, we can bound this number by q to the b2n plus 1 for some exponent b2. And in all the other cases, we can bound it by this expression here. And let me just say both of these exponents can be upper bounded by a polynomial function in n, and b3 is actually already a polynomial function in Bn. And moreover, both of them are always greater or equal to 0. Now, using these 3 cases here, we can get this following expression here. And how do we do that? First, I restrict to the case that k is between 0 and n over 2 floored, because we can with these 3 cases. So this explains the 2 in the bracket. In the bracket, the last one stands for the k equals 0 case. This expression here comes from the k equals 1. And this expression here comes from the rest. So what is the rest? The rest is 2 to n over floored minus 1 many. N over floored many, so that there are n over floored minus 1 many cases, which are in this case here. And these n over 2 floored minus 1, we simply upper bound by n over 2. So this explains this expression. But now, if you look at this expression, this is just a bound which is at most exponentially. So we actually succeeded and with our second task, which means in conclusion that we can prove our theorem. Since we have something exponentially over something double exponentially, this limit will vanishes as n goes to infinity, and therefore proves our theorem. And yeah, that's it. Thank you very much for your attention. And yeah.
We have time for questions again.
I'm wondering whether a lower bound on number of matroid implies lower bound on number of q-matroid.
So I don't think so, because it's not that easy to associate to a matroid a q-matroid in general. Yep. What?
What is the exponent?
The exponent, yeah, it's. What do you mean? Yeah, it's polynomial. And the power, the highest power, 2, I guess. I hope. If I remember correctly, it's 2. Yeah.
There will be some announcements before the coffee, but let's first thank Sebastian a second time.